welcome to this video for EDEXCEL Topic 9, Kinetics 1. My name is Chris Harris and I'm from AlleryTutors.com, and basically in this video we're going to do a overview of Topic 9 for the EDEXCEL specification. It's mainly designed for revision to give you an idea of the type of stuff that you need to know for Topic 9 in particular. These slides that I'm going to be using here, they are available to purchase. They're great value for money. And you can use them as revision. You can also get them as bundles, so you can get them all bundled together, the whole lot, the whole AS, so the complete revision package. If you just click on the link in the description box, you'll be able to get a hold of them there. So like I say, these are dedicated to EDEXCEL in particular, and so they meet the specification, and these are the specification points taken from the EDEXCEL syllabus, so it meets that. Okay, so let's have a look at rate and collision theory. So for a reaction to occur, the particles must collide. So we're going to look at rate of reaction. So rate of reaction is basically the change in concentration or the amount of a reactant of product per unit time. So that could be per second, per minute, per hour, whatever the time is that we're using. So rate is the amount of reactant used or product made, it doesn't really matter which one, over time. Okay, you've got to know that equation. It's really, really important. Okay, so the particles, they move all the time and they collide into each other. So it's very hectic in this atomic world. But most collisions actually don't lead to reaction. So they kind of bump into each other and bounce off each other, but they don't actually react. So collision theory is kind of born about this idea. Okay, and collision theory states that for a reaction to occur, the particles must collide in the right direction. And they must also have the minimum amount of kinetic energy. And for those physicists who are out there, you'll know kinetic energy as being moving energy. So they must basically have a minimum amount of energy for them to collide. Now, obviously, we're going to be talking a lot more about this as well. So that's just like the basic overview. But we're going to now look at some what we call energy profile diagrams. Okay, and the minimum amount of energy required for a reaction to occur, remember this was the collision theory we just talked about there, is called the activation energy. So this is an energy profile diagram. It basically shows the energy change within a reaction. It's just a way of trying to show it, really. Now you can see here, we've got a diagram here showing enthalpy and reaction progress. And we've got reactants here and products here. And you see the reactants are higher in energy than our products. So what happens here at this point in our energy profile is the molecule bonds are stretching as they have more kinetic energy. So we must have given them a little bit of heat and they're starting to move a little bit more. Now, this gap here between the energy of the reactants and the top of the profile is called the activation energy. Okay, remember this is the minimum amount of energy required for a reaction to occur. Okay, so the reactions are, obviously the particles are colliding, but this is the amount of energy needed for a reaction, an actual reaction to happen. And so obviously at this point, the bonds have enough energy for them to break at the top of the profile. Now reactions that have low activation energies, they need less energy for them to actually break the bond. And obviously the energy normally comes from heat and vice versa. Okay, so we're going to look at something called a Maxwell-Boltzmann distribution. So Maxwell-Boltzmann distribution shows the energy in gas particles. Okay, so the particles of gas in a sample move at different speeds. They're not all moving at the same speeds. They're all at completely different speeds. Some moving quickly, some moving quite slowly. And they have different amounts of kinetic energy. Really important that you need to kind of just try and visualize these atoms in a box. They're all moving around, but they're not all moving at the same speed. It's a bit like a motorway. Okay, cars are moving at various speeds. Some are going at 60, some are going at 70, some might be going a lot slower than that. So some might be going quicker as well, which is obviously against the law, but never mind. You've basically got different speeds. Particles in a box, gas particles are the same. Okay, so if we plot this on a graph, we get a Maxwell-Boltzmann distribution. Okay, so they look a bit of a funny graph, but they have these axes. We've basically got a number of particles going up here. And we've got kinetic energy, okay, going along the bottom here. Now we're going to point out some certain things here. The graph starts at 0, 0, as you can see here, because no particles have zero kinetic energy. They must have some kind of energy. And the area under the curve, this bit here, is equal to the total number of molecules that we've got in our sample. Okay, and that obviously remains constant throughout all of this. Now, the peak bit at the top, this is the most likely energy of a particle in a sample. So if I take a particle, what is the most likely speed well, the most likely energy that that particle would have. Because obviously we're talking about kinetic energy, and kinetic energy is linked with speed. So it's basically the most likely energy a particle will have in that sample. However, just to the right is the mean energy the particles have. Okay, we've really got to distinguish between the difference between them two. So most likely energy and the mean energy. Okay, it's always just slightly to the right of the peak. Now this point here is the activation energy. This is always to the right of both of them, and it's normally quite far over to the right, as you can see in this diagram. Okay, these particles over here on the left, they have very little energy. They're moving pretty slowly, whereas the ones in the middle here, they have moderate speeds. They have a little bit more energy, and this area here, these have energy greater than the activation energy. You can see they are to the right of the activation energy. So these particles have enough energy for them to react. And so these will obviously go on to form products. But you can see here the vast majority of particles don't have enough energy to react. But just a small proportion do. Okay, so let's have a look at what affects rate. So temperature affects the rate of reaction. So particles, on average, they have more kinetic energy when they're heated. Obviously, we're giving them some energy from thermal energy. So a larger proportion of the molecules will have energy greater than the activation energy. This is symbolized by the red line, as you can see on there. There's a larger area under the curve beyond the activation energy, but the overall area underneath the curve is the same. So you can see here, we've increased the area underneath the red curve beyond the activation energy. So we have more particles with energy greater than the activation energy. So very important points here, okay, because I might get you to draw this. The first point is the curve shifts to the right, okay. Second point, the peak is lower than the molecules at a lower temperature. The area under the curve is exactly the same as the area under the curve on the white one, because we've got the same number of particles. And the area under the curve beyond the activation energy does increase though, so it is higher than the other one. So you've got to make sure you're meeting all these points here when you're drawing a curve at a higher temperature. If we do the opposite at a lower temperature, so we decrease the temperature, we've got a smaller proportion of the molecules that have energy greater than the activation energy, smaller area under the curve beyond the activation energy, which is this yellow line here. You can see here, there's the blue one, much, much smaller area. But crucially, again, you know these points, the curve now shifts to the left in comparison to the white one, which is at normal temperature. The peak is a lot higher, so we've got a higher chance of particles having energy. This is the most likely energy the particles will have, which is going to be a lot lower because obviously we've cooled it down. Area under the curve, though, overall is the same as the one under the white one, and but the area beyond the activation energy decreases. Okay, so why do we get a faster rate of reaction when temperature is increased? So we need to go onto a molecular level here. So what happens is particles, they move around more at higher temperatures. Okay, so they collide more often, and obviously this is the reason why they happen more, why reactions happen faster at higher temperatures. These are all whizzing around much, much more energy and colliding more often. Now the combination of more collisions and more energetic collisions, because they've got more energy as well, means that just a small increase in temperature can have a large increase in the rate of reaction. And obviously we're looking at these two factors here. So we're looking at the likelihood of the of more collisions, happening, and we're looking at the more energetic collisions as well, means that we get a much, much bigger increase in the rate of reaction. Okay, concentration pressure, this also affects the rate as well. So increase in the pressure will increase the rate of reaction. Particles are much closer together, they collide more often, and there's more frequent collisions, or there are more frequent collisions, and so therefore we've got a higher chance of reaction. You can see here this is at low pressure and this is at high pressure, and you can see that the particles are much closer together, much higher chance of collisions here, and so that's why a high pressure will lead to a faster rate of reaction. Whereas if we look at concentrations, very similar to pressure, except this is mainly to do with liquids though, or solutions, should I say. So increase the concentration, increases the rate of reaction. The particles, you can see, are much closer together. They collide more often, more frequent collisions, and so therefore we've got a higher chance of a reaction. And you can see here, here's the higher concentration. Look, there's a lot more red circles. They've got a much more likely chance of them colliding with each other. than compared with the blue ones here. Compared with the red ones here, where you've got more blue circles. So we see much higher. So it's very similar. Concentrations mainly for solutions though. Okay, catalysts also affect rate as well. Basically what they do is they increase the rate of reaction. What they do is they provide an alternative pathway, and that pathway has a lower activation energy. Okay, really important because that means we've got less energies needed to get this reaction to go. Crucially though, a catalyst is chemically unchanged at the end of the reaction. So if, for example, certain catalysts are actually involved in the reaction, they're used up, they're reformed at the end. Okay, it's a classic sign of a catalyst. So they're used to speed up a specific reaction. We have different catalysts for different reactions, so you might see a variety of different catalysts. They're used to make the product faster. They can lower the temperature required, so that means for industry it saves energy, and obviously that saves money. You don't need to heat them up as much. And here's an example of a catalyst. This is a zeolite catalyst. Zeolites have a large surface area. Obviously surface area is really important here. The larger the surface area, the more likely you're going to get a reaction to occur. And zeolites are an example of they've got micropores inside these, which allow reagents and reactants to kind of get involved. Okay, so the types of catalysts. So they can be homogeneous or heterogeneous. So heterogeneous, this means that the catalyst is in a different phase from the reactants. Okay, so it's in a different state. So an example could be Haber process. So we've got nitrogen and hydrogen, obviously that's a gas. We'll produce ammonia, which is also a gas. We use a solid ion catalyst. Obviously this is in a different state to the reactants and products. And so obviously this is classed as a heterogeneous catalyst. Now with heterogeneous catalysts, if we increase the surface area, particularly for solids in particular mainly, if we increase the surface area, then the catalyst will increase the rate of reaction. We've got more particles that can react at the same time if we increase the surface at which these particles can absorb, which we'll look at later on. Okay, so homogeneous catalysts, these are basically catalysts that are in the same phase as the reactants. So generally these homogeneous catalysts are aqueous-based reactions, aqueous-based catalysts, and they're interacting with aqueous-based reactants. So sulfuric acid to make an ester is a classic example of that. Now these form an intermediate. They're slightly different in their reactions. They form an intermediate species. They combine with the catalyst, the actual reagent, to form the product, but crucially the catalyst is reformed again. So they kind of react in a slightly different way from heterogeneous to homogeneous. Okay, so let's have a look at this heterogeneous catalyst in a little bit more detail. So substances, what they do is they adsorb. That's with a D, not with a B. Okay, so that isn't a spelling mistake. So adsorb to the surface of solid heterogeneous catalysts. So reactions occur on solid heterogeneous catalysts. They bond with the surface. Okay, like I said, we call that adsorption. So the bonds in the reactants weaken and break to form radicals. Okay, so these are atoms or molecules with that unpaired electron, if you can remember. And the radicals then react with each other to make new substances. So you can see, there'll be a diagram that I'll show you in a minute, and you'll see how it adsorbs on. But the new molecules are then released from the surface of the catalyst, and this is a process called desorption. So this is it leaving the surface of the catalyst. So we're going to have a look at a specific example. So with this reaction, we're going to look at the formation of ammonia using iron as a catalyst in the Haber process. So here it is here. Here's your iron catalyst surface. Okay, and you can see we've got obviously nitrogen and hydrogen obviously sticking to the catalyst surface. So this is called adsorption with your D. And you can see here what happens is they then desorb. And you can see here that the ammonia obviously breaks free, and we've got our molecule here. And this is effectively what happens with a catalyst. So it holds on to the reactants, and then they desorb. Okay, so we'll have a look at the energy profile as well for heterogeneous catalysts, because this is just as important. Okay, so let's have a look at the Maxwell-Boltzmann distribution. Now, you can see here that the catalyst lowers the activation energy. So we've got more particles now have enough energy to react. You can see that it's shifted over to the left now. So this is an uncatalyzed reaction, and this is a catalyzed reaction. So we have many more particles with energy greater than the activation energy. But looking at it in terms of an energy profile diagram, you can see here that we have an activation energy with no catalyst, which is here, as you can see. So we've got this energy profile here. And then obviously, if we add a catalyst, that lowers the activation energy, so the rise is a lot less higher. So we need less energy for effectively for our reaction to go. So that's the effect of a catalyst on our energy profile diagram. Now this is for a heterogeneous catalyst. Okay, so this Maxwell-Boltzmann on this side also applies to homogeneous catalysts as well, so it's just the same. Okay, as for homogeneous catalysts, these have a slightly different energy profile. Okay, these actually have two activation energies. Okay, and this is because, remember, they form this intermediate, like we say. Okay, so here's our energy profile diagram. Now you can see here, this is our reaction that's uncatalyzed, and this is the activation energy. Obviously, it rises up to the top there, and then it drops back down to our products. But when we add a catalyst, we get this like double bump. Okay. So you can see here the catalyst has obviously lowered the activation energy, so more particles have enough energy to react. But notice we've got an activation energy with the first, with the catalyst. This is the first step, and obviously what we form is this intermediate. Then the intermediate then has to break up to form your products, and we need a little bit of energy to do that as well. And this is obviously the activation energy of the catalyst with the second step. So homogeneous catalysts have this double bump, as you can see in there. Okay, so your intermediates are represented by the dip between the two bumps. Obviously, you can see in the reaction profile there. Okay, so why do we use a catalyst? Catalysts are pretty useful in industry, to be honest. So what they do is they lower the temperature needed for the reaction to happen. This means you've got less money being spent on fuel to heat the reaction, and also for the environment, we're using less CO2 because normally the fuel is fossil fuel based. Speed up the reaction, they provide an alternative pathway, so that means you get your product quicker, and as they say in industry, it's time is money. And also, they can actually change the properties of a product, so these are pretty special catalysts. So for example, Ziegler-Natta catalysts, what these do is these turn polyethylene, again that's a bit of a typo, it should be ene, polyethylene, to a more dense, rigid and higher melting point plastic. Okay, so they change the properties of them. So that's just my autocorrect. That's my autocorrect as you kick it in. Okay, so that's polyethylene. Right. Okay, so there are environmental benefits as well for using the catalyst. Like to say, lower temperatures and pressures are required, so we need less carbon dioxide is emitted from using the fossil fuels to do that in the first place. Also, less waste is produced because catalysts allow us to develop reactions which have better atom economies. So instead of producing a product, for example, via 5 steps in a catalyzed reaction, in an uncatalyzed reaction, if we use a catalyst, we might be able to do it in 2 steps, for example. That means we've got less waste and we're not transferring reactants from vessel to vessel. So it's just a lot more efficient doing it that way, and catalysts can help us do that. Now, you might have heard of catalysts in cars, very common in cars or vehicles. These are catalytic converters. They're basically designed to remove pollution that's produced from burning fuels in a car, like petrol and diesel. And so they are made from rhodium, platinum and palladium alloy, so it's a mixture of all these metals. And what they do is they convert poisonous gases like carbon monoxide and nitrogen monoxide into less harmful ones. They're still not great, but carbon dioxide is obviously a greenhouse gas, but it's better than carbon monoxide. Nitrogen is not a problem because that's naturally found in the air anyway. So we're producing these less harmful products. Okay, you can see here, just in case you were interested where you might find these, if you look in the front bit of the car, underneath the engine bit, where the exhaust obviously runs underneath the car, catalytic converter is just a box, part of the exhaust system, and it's obviously just found in there. But it contains very precious metals, so they're quite expensive. Okay, so how can we measure the rate of these things in experiments? So we can look at how long it takes a precipitate to form. So if your reaction is producing a precipitate, we can place a cross on the paper and time how long it takes for it to disappear. You might have done this with your sodium thiosulfate reaction, for example. Problem is, it's really difficult to know exactly when that cross disappears. It's open to perception. It helps to try and use the same observer when you're doing this. It just reduces any errors. But again, it's not great. It's not a brilliant reaction. Another one we can do then is using a mass loss. So if we're producing a gas, this is really useful for producing a gas. All we do is you take our flask, put it on a top pan balance, and measure the mass loss of the reaction. It's a fairly accurate method. However, we've got to use a fume cupboard. If the gas is produced, it's toxic. You don't want to be breathing this stuff in, so there obviously are limitations to it. More usefully, actually, we can measure the volume of a gas produced. So basically, we just set our reaction away. If a gas is produced as a product, then we can measure how much of this gas we produce over a specified amount of time. Remember, that's what rate is. It's the rate at which, rate is basically the amount of product produced over a given time. Okay, so we always have a time element to this as well. Okay, so this is pretty useful and probably more common that you'd see, especially when you're producing a gas, is a rate of reaction measured using this. Okay, obviously we can use this results and we can plot results on a graph, and then from that graph we can calculate the rate. So rate can be found using the gradient of a graph. So you can see here that we've got the volume of a gas produced. You can see here that we've got a straight line graph and we've got the time in minutes. Now the gradient is the change in y over the change in x. So remember, this is your y-axis along here. That's your x-axis along the bottom. So basically, the bigger the section of the graph that we can use to work out the gradient, then the better. Basically, your results will be a lot more reliable if we're using a bigger triangle. So try and do that. What we need to do is try and find points in the graph where the change in y and x can be worked out easily. You know, make your life easier. Don't go for like halfway through a line or something. So let's have a look. Let's go for that one, for example. So we're going to go along here and along here. And we're going to measure the difference. So the difference there is a difference of 6. This is obviously in minutes. And the difference here is a difference of 4. And obviously this is the volume of gas produced. So the change in y is going to be obviously 4.6, that's here, minus 0.6 because that's down here. So that's the change, obviously that gives us 4. And the change here is going to be 7, which is here, minus 1, which is here. So that obviously gives us 6. And that gives us a gradient of 0.67, and obviously that is our rate. Now this is centimeters cubed per minute. Okay, that's how we work out units. Look at the units on your axis to help you work that out. Okay, sometimes you don't get straight lines though, and we get curves. We have to draw a line of best fit. So what we have to do is work out the gradient of a tangent for something like this. So it's getting very mathsy here. So with curves, obviously we draw a tangent, which is just a diagonal line that meets a very specific point on that curve. We extend the line right across the graph, and that allows us to work out the gradient. And the gradient is just the rate at that very specific point on the curve. Okay, we can't say that the rate is the same because it's obviously curved. The rate is changing as we go along. So in this example, we're going to work out the rate of reaction at 3 minutes. So which is here. So we want to work out the rate of reaction at that specific point there. So we draw a tangent there. There it is. Okay, so literally it just hits where it says 3 minutes. There's our tangent. We extend it right across fully. Then, using the same thing, gradient is the change in y over the change in x. Okay, so the change in y, again, make it easier for yourself. Okay, so there's the change in y. There's the change in x, which is 4. So we've got 0.8 and 4. And this is basically how we've worked it out. So we've just done 20.8 minus 20.0, which is that difference there. And then obviously the difference between 0 and 4 is just 4. So the gradient in this case is 0.20. Notice though, we're using different units. It's grams per minute. Okay, just use the units on the axis to help you work that out. Okay, sometimes it's more useful though to calculate an initial rate, okay, from a reaction. So initial rate can be found by using the gradient of a tangent, just like what we've seen before, okay? But the initial rate is the rate right at the start of the reaction. So this is right at the start. And just like before, we're going to take the gradient right at the start of the tangent, okay? So we're going to take it at 0 minutes because this is right at the start. So tangent in 0 minutes would look like this. There it is, incredibly steep, as you can see. Really steep tangent. Gradient, again, is change in y over change in x. So let's mark it out. There it is. So we're going to go for this one because it's probably the neatest one. It's the easiest one we could probably measure. We're going to measure the difference, 1.7, which is the difference going on the change in y. Change in x, the difference is going to be 1. And you can see here that the gradient is then going to be 1.70 grams per minute. Again, we've got the mass in grams over minutes. So initial rate is pretty useful because we can compare, a lot of reactions are done by our initial rate and we can compare them against other reactions. So yeah, so make sure you know where the initial rate is and how to work it out. And that's it. That's just a quick overview of topic 9 in Kinetics 1 for EDEXCEL. Please show your support for the channel. Really appreciate it if you just subscribe to it. It doesn't cost anything. They're all free. You get all the updates on videos that we upload. If you just click on the middle button, you can subscribe there. It'd be much appreciated. And like I say, you can purchase these slides. Great value for money. Enhance your revision. Help you to get them top grades. If you just click on the link in the description box, you'll be able to get a hold of them there. But that's it. Bye bye.